Let's do 3 examples using our derivative rules for our inverse trig functions. Starting off with the inverse cosine of 1 over x. All right, well, y prime is minus 1 all over the square root of 1 minus u squared times the derivative of u. The derivative of 1 over x is 1 over x squared. I'm really just thinking about the power rule. 1 over x is x to the minus first, and that tells me there should actually be a minus up there, so minus 1 over x squared. And I want to simplify this a little bit, and there's more than one way to do this simplification, but I'm going to say minus 1 times minus 1 would be a positive 1, all over x squared times the square root, and under the square root, I want to find a common denominator. So this one, I'm going to think of x squared over x squared. I can now imagine factoring out the square root of 1 over x squared. I'd have that x squared on the outside times 1 over x times the square root of x squared minus 1. I can reduce, and I'll have 1 over x times the square root of x squared minus 1. And there's my nice happy derivative formula. Moving right along, now I need to follow the rule for inverse tangent to take the derivative of y equals tangent inverse of the natural log of x. So y prime is equal to 1 over 1 plus u squared times the derivative of u. The derivative of the natural log of x is 1 over x. And I'm going to rewrite this just a little bit, but really that's about all I can do. I'm just going to think about distributing that x. And there's my derivative for inverse tangent of the natural log of x. And our final example, take the derivative of arcsecant of 5x. Following the rule for secant, inverse secant that is, y prime will be 1 over the absolute value of u times the square root of u squared minus 1 times the derivative of u. And if I think about it, the absolute value of 5 is, well, 5. So I have a 5 on the top and a 5 on the bottom. So I can just rewrite that as the absolute value of x times the square root of 25x squared minus 1. And those are my 3 examples using the derivative rules for our inverse trig functions.